pleasure to make the presentation about our paper, FalCon, the fine-grained feature map sparsity computing with decomposed convolutions for inference optimization. I first talk about the paper motivation. As we all know, the convolutional is actually the matrix multiplication between the feature maps and the filters. So the feature map and filters are equally important during the convolution operation, and tons of the work will proposing to identify the redundancies inside the convolution and try to optimize the model inference. However, most of the works are filter redundancy pruning, and a few works tackle the feature map redundancy pruning. And our work is actually doing the feature map sparsity optimization. Also, if we review the sparsities on the feature maps, we will find that the practical sparsity patterns are actually non-structural, randomly located, and distinct among each feature map, and they also have the fine granularity. However, the current feature map sparsity work can only remove the entire channel or the spatial column due to the hardware efficiency constraint. So that will introduce a gap between the coarse grain, the feature map sparsity work, and the fine grain, the practical sparsity pattern. So our work is trying to find the method to achieve the fine grained sparsity while maintaining a hardware efficiency. So we first do the propose the decomposed convolution. The left picture shows the traditional feature map convolutional operation, and which is filter based. We can see each filter will interact with all the feature maps at the same time to do the convolution operation. We then decompose the convolutions in the channel wise. So after the decomposition, each feature map will only conduct individual convolutions with the filters belong to the center channel. Sorry, the kernels belong to the center channel. And the basic operation unit is refined to the kernel size feature map arrows, which will become to the each columns on the feature map matrix. And such decomposition has two advantages. The first is the flexible location. The kernels are sliding on each feature map, and our kernel-wise computing unit can locate it at any spatial column of the feature map matrix, as it shows. The second one is the fine granularity. The most widely used neural networks usually adopt a small kernel size, so it will have the fine-grained sparsity to match the practical sparsity pattern. However, our kernel-wise computing unit will randomly distribute on the feature map with unbalanced sparsity ratio and non-zero columns, and so become the non-structural and computing inefficient. Therefore, we further propose the computing optimization paradigm to achieve the hardware efficiency. First, we will do the channel-wise sparsity regulation to let the sparsities on each feature map identity. The sparsity ratio on each feature map are identical. Then we do the sparsity reordering to merge the sparsities on each feature map together to get the continuity non-zero value. Then we do the matrix truncation to remove the sparsity and to get the much smaller feature map matrix. Then we recompact them together to do the general matrix multiplication. We've evaluated our method on the different data sizes and models, and our methods could generally achieve 44% to 67% flips reduction with this 1% accuracy drop, which significantly outperforming the previous state-of-the-art works. We also evaluated our method on the GPU and the CPU and shows the acceleration performance.